Hey, welcome back. So in the last section, we looked at elementary reactions and the fact that we can indeed write rate laws for the elementary reactions, which I think is really cool. And in this section here, we're going to use this information to figure out how fast a reaction will be. And we're going to make use of this idea that isn't always present in every single chemical reaction, but when it is, it makes writing the overall rate law very simple. And that is the idea of a rate determining step or a rate limiting step. So we can write RDS or RLS for short. And what we find is that there's often in a chemical reaction a bottleneck. There's often a reaction, or an elementary reaction I should say, that is so slow it affects the rate of the overall reaction. So a classic example is as follows. So there's some road construction on a highway, and you're driving along, and so it's a 3-lane highway, so you can drive along, brum, 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 and you go down the road, and then there's a bunch of cones, and so all of a sudden now you're all forced to use a single lane. So of course, the fact that you're all moving into the same lane means that this speed here and the number of cars that can go through here is really the number of cars that can make it down the other end of the highway. So you've got a construction zone, right? You've got a bottleneck, and this bottleneck is going to determine how many cars can get through to the other end of the highway. So we find this in the chemical reaction. There's often a mechanism, there's a step in the mechanism that's really slow, and that slow step is going to affect the rate of the overall chemical reaction. Okay, let's take a chemical example here. So we looked at an overall reaction a few videos ago. We said that ozone can decompose and form oxygen via this stoichiometric equation. And we proposed a mechanism. So we proposed a series of elementary steps that take us from reactants to products. And that is that ozone can break down and form dioxygen and an oxygen atom. And that oxygen atom can react with a second ozone molecule and form 2 oxygen molecules. Now, it turns out that the first reaction here is actually quite slow, and the second elementary reaction here is actually kind of fast. So we can say that the first step is the rate determining step or the rate limiting step. So if we look at this chemical reaction here, imagine this ozone breaking down is very, very slow, but once it's broken down, this oxygen atom reacts extremely rapidly. So the overall rate of the reaction is going to be determined by how slow this first step is. So we can say that the rate of the overall reaction is just the rate of the elementary reaction. Now, the rate of the elementary reaction, we now know how to write. So the elementary reaction 1, has a rate that is equal to K times the concentration of all the reactant molecules colliding multiplied by each other. So since there's just one, right, it's just rate equals K times that one thing, which is ozone. Do you remember what this molecularity is? That's right, it's a unimolecular reaction. So we can go ahead and we can say that the rate of the elementary reaction, if it is the rate determining step, is the rate of the overall reaction. So the overall rate law, for the reaction then is just the rate of the first step. So it's K times by O3. Now, if we go into the lab and we do an experiment, what we find is that the experimental rate is in fact K times by O3, right? So we say it's first order overall. So our prediction, matches reality. So the question is, did we prove our mechanism? And the answer is kind of, sort of, probably, honestly, no. So we may have just gotten lucky. We may have written a mechanism that coincidentally has exactly the overall predicted rate that the experiment gives us. But we can certainly say if the predicted mechanism gave us a predicted rate that wasn't matched, it couldn't be possibly correct. But it may be a stopped clock is right twice a day. So it may be the situation where just through sheer coincidence, it is giving us the exact same rate law, but we can't necessarily say it is exactly correct. Now, it does give us a chance to make a prediction that we could test in a lab. So our mechanism is showing us that we should have these oxygen atoms as intermediates. And so maybe we can detect them spectroscopically. Maybe they absorb light of a particular color. We can use an ultra-fast pulse laser that's tuned to that oxygen atom. And if we see it kind of build up and disappear quickly in the reaction, it gives us a little more confidence our mechanism can be correct. But unfortunately in science, we typically can't prove things are correct. We can only disprove. So even though our mechanism matches reality, we don't necessarily say that means our mechanism is proved. Unfortunately in science, we can only disprove. If it didn't match, we could say it certainly isn't. If it does match, we can say maybe.